All right. So this is going to be a presentation of Euclid's proposition 47 from book one, which is better known as the Pythagorean theorem. Sorry. Okay, so throughout this presentation, what I'm planning to do is in the sort of top right corner here, I'll have the listed out the propositions that are incorporated in the steps on that slide. So for this slide, we're going to use Prop 46, Prop 31, and Prop 14 in that order. So to begin, recall what we're trying to prove is that if we're given a triangle ABC, which is a right triangle, we want to prove that the sum of the squares on the legs is equal to the square on the hypotenuse. So to begin, the first thing that we're going to do, of course, is create these squares on the legs and on the hypotenuse, and that comes from proposition 46, from a given straight line to describe a square. Next, we're going to construct a line through A parallel to BD. We call this line AL. So AL right here, this is from Prop 31 to draw a straight line through a given point parallel to a given line. So we're drawing AL through A parallel to CE, and of course, if it's parallel to CE, it's also parallel to BD. Next, we will connect points AD as well as FC, which that's not listed as a proposition. That's really just a postulate. I think it's the first postulate. And we're going to mention or observe that if we look at angle GAB right here, so it's this angle of this square right here, right next to that is angle BAC, which we know to be a right angle. We also know angle GAB to be a right angle since this is a square. And by Prop 14, if we have two right angles adjacent to each other, that means that there's a straight line being formed. So this line from G to C, that is a straight line. Similarly, we have that angle BAC is a right angle and angle CAH is also a right angle. So again, we have these adjacent right angles making BH a straight line. And this might seem like it's kind of coming out of nowhere and maybe seems sort of purposeless, but this will be a useful fact in a couple of steps here. Okay. So next, notice that angle ABD, so the wide angle of this purple triangle, we can rewrite angle ABD as being angle DBC plus angle ABC. So this corner of this square plus the top of our given triangle is angle ABD. And similarly, angle FBC, which is the wide angle on this green triangle, can be written in a very similar way. We can write that as angle FBA plus angle ABC. So the top of this square, this corner of this square, plus the top of our triangle. But recall, since these are squares, we know that angle DBC, so the corner of this square, is a right angle, and so too is angle FBA. So these are both right angles, and because the way that we've written out angle ABD and angle FBC also, they share this common angle of ABC, and as we just stated, DBC and FBA are both right angles. That means that the sum, since equals being added to equals, that's common notion too, equals being added to equals, the wholes are equal. This results in angle ABD and angle FBC being equal. So again, they share angle ABC and they both have attached to angle ABC a right angle. So angle ABD is equal to angle FBC. So the wide angle of the purple triangle is equal to the wide angle of the green triangle. And finally, because side DB is equal to side BC by construction, side FB is equal to side BA by construction, and because, as we just have shown, the angles between those sides, the angle between BD and FC, and the angle between FB and, the angle between DB and BA, and the angle between FB and BC. Because those angles are equal, we have the side angle side congruence, meaning the purple triangle is congruent to the green triangle by proposition 4, side angle side. Okay, so with that in mind, we now are going to use Prop 41, which says that if a parallelogram has a base that's the same for a triangle and both the parallelogram and the triangle are in the same parallels, then the parallelogram is twice the triangle. It's double the area of the triangle. And if you look at first look at a parallelogram, or I guess it's a rectangle, BZLD, this purple rectangle. This is falling in the same parallel and has the same base as triangle ABD. So the base that they share is BD right here, and they both fall in the parallel lines BD and AL. So using Prop 41, that means that triangle ABD is half of the rectangle BZLD, or that BDLZ is twice triangle ABD. Same thing over here. If we look at this square GABF and we observe that GABF shares a base with triangle FBC, namely line FB right here, and they both fall again in the parallels FB and GC, then we have the same relationship there, that square GABF is twice FBC. And this is where, from like the very first slide, we had we proved that these are just straight lines. GC is a straight line. This is where that comes in handy, because otherwise there would be the question of, well, how do we know that GC is a straight line? Because here I'm claiming that GC is parallel to FB. Certainly GA is parallel to FB, but we don't know that GC is parallel to FB unless we've shown that this is just a straight line. And it is, meaning that square GABF is equal to twice triangle FBC. And then, because we've already shown that triangle ABD is congruent to triangle FBC, it follows that rectangle BZLD is equal to square GABF. So these purple areas are the same. Now, all that needs to be shown is that this remaining square, HKCA, is equal to the white part of the hypotenuse square, CELZ. And so that's exactly what we're going to do next. And we're going to do it in a very symmetrical way. So we'll start off by joining AE and BK. Notice that angle ACE, so the wide angle of this purple triangle, is equal to angle ACB plus angle BCE. And similarly, angle KCB, which is the wide angle of this green triangle, angle KCB can be written as angle ACB plus angle KCA. And once again, we're in a position to say, well, these two angles are the same. Why? Because they share this angle ACB, and we know that BCE and KCA, they're corners of squares. So they're both right angles. So once again, we have equals being added to equals. So angle ACE is equal to angle KCB. And then we're going to invoke side angle side once again to show that these triangles are the same. So AC by construction is equal to KC. Side CE is equal to side CB by construction. And then the respective angles between those sides in each triangles, which we just showed, angle ACE and KCB, are equal. So by side angle side, once again, the purple triangle and the green triangle are congruent. And now, once again, we can use Prop 41 with our parallelograms and triangles in the same parallels. So CELZ, this sort of brown-orange rectangle right here, falls in the same parallel and shares the same base with ACE. So they both share this base CE right here. They both fall in the parallels CEAL. So rectangle CELZ is equal to twice triangle ACE. And then square HKCA shares a base with triangle KCB, namely the side KC right here. And we know that KC and HB are parallel. Again, because we have shown that HB is just a straight line. So KC and HB are parallel since both HKCA and triangle KCB share the same base and are between those parallels. HKCA is twice triangle KCB. And because on the last slide, since we had shown that triangle ACE is equal to triangle KCB, it follows that rectangle CELZ is equal to square HKCA. So these brown-orange areas are the same. And so we just put it all together now. We've shown that BZLD, the purple rectangle here, is equal to GABF, the purple square. We've shown that CELZ, the brownish rectangle, is equal to the brownish square, HKCA. So adding these together, we see that this larger square BCED, which is the sum of the purple rectangle and the brown rectangle, we see that BCED is equal to the sum of the squares GABF and HKCA, which is what we set out to show to begin with.